Welcome. Take a seat and grab something nice to drink. Today I want to talk about something my little brother asked me a few days ago. He asked me why negative powers were the way they were. He asked me specifically, why was it that 44 to the minus 1 is equal to 1 over 44? Well, I thought the answer would be easy, but turns out not, and there's some really interesting stories here. So let's figure out why negative powers are the way they were. Let's go to the basic definition of what a positive power first is. A to the power of n, where n is a positive whole number. We first learned that it represents the product of n a's. And that this only works for a greater than 0 whole number n. And while working with these powers, they're quite convenient because you don't have to write down NAs. You could just fiddle with the exponent. And more precisely, there's this additive property that if we had a to the power of n plus m, that's going to be equal to a to the power of n times a to the power of m. Intuitively, the product of n plus m a's is equal to the product of n a's times the product of m a's. Okay, so that's still nice. Additivity is really cool. And this is for n and m greater than 0. While working with these, we might stumble across another property, which looks very similar to additivity, which is that a to the n minus m is equal to a to the n divided by a to the m, provided n minus m was a positive number. So I'm going to write that as n is greater than m, which is greater than 0. So this is saying that if we had the product of n minus m a's, it's the same as the product of n a's, except we want to take away m of those a's. So we'll divide through by a to the m. Okay, so here we look at the condition for subtractivity, and we could do a thought experiment. This condition looks kind of annoying. Could we loosen it up a bit, make it so that n and m could be freer? They don't have to be constrained by this inequality. So let's think about the other cases of n's relationship with n. M's relationship with n, or n's relationship with m. So let's first look at the case where n equals m. Then a to the n minus m, or I'm going to write a to the n minus n, is equal to, according to our subtractivity equation, well, it should be equal to this for subtractivity to keep working. Okay, well, the left-hand side, the n minus n, that's 0. And the right-hand side, a to the n over a to the n, so long as a is not 0, we could safely say that this is 1. And from here on, we're going to assume that a is not equal to 0, because 0 is a bit of a special case. Okay, so this is interesting. We've suddenly popped up with a to the 0 equals 1. And this is the definition of a to the 0 mathematicians tend to use. It's a definition because it doesn't follow our original definition that a to the n is the product of n a's. It doesn't make sense to say the product of 0 a's. But we could define the product of 0 a's, or a to the 0, to be equal to 1. And we make this definition because this satisfies subtractivity and additivity, which are our two important exponent laws. And also, this is a unique solution. There's the only a to the 0 that satisfies these two laws is a to the 0 equals 1. It's the only reasonable choice, and that is really important. And it explains why 0 to the 0 doesn't, we can't really make a nice definition. So let's think about 0 to the 0. 0 to the 0 should be a number x such that 0 is equal to 0 times x. Okay, but then the solutions for x in this equation could be anything. Hence anything times 0 is equal to 0. So here x is not unique. And so if we wanted to have this fraction law be satisfied, there's no sensible unique choice to make for what 0 over 0 should be. So then it feels a bit weird. So mathematicians don't like to talk about it. Okay, so let's take this idea further. Let's extend subtractivity to the other case, when n is less than m. Okay, well here it's going to say a to the n minus m is equal to a to the n over a to the m. And I'm going to set n to be equal to 0. Then what happens is that here on the left-hand side we get a to the 0 minus m, which is a to the minus m. And that should be equal to a to the 0 over a to the m. Well, we just worked out that we just made a new definition that a to the 0 should be 1. So a to the minus m is 1 over a to the m. So this is exactly the definition of negative powers mathematicians use. And this is really cool because this is again unique. So it's the unique negative power definition that satisfies subtractivity and additivity. It extends our useful properties, it doesn't break anything, and it's also the only sensible choice. We like it. So a challenge for you then is to try and extend these ideas further. What if a were equal to 0? I said earlier it's a special case. In what sense is it special? Do 0 powers, negative powers still make sense? What if n were not just like whole numbers? What if n were a fraction of whole numbers? How should we define powers that way? Is there a sensible definition? What if n were an irrational number? What if n were not even irrational, but transcendental? Or what if n were not even transcendental, but complex? So this is kind of a hierarchy, and if you don't know what irrational numbers or transcendental numbers are, this could be a good chance to like get your feet wet, to learn about what these things are. They have very cool names, that's for sure. So if you have any thoughts, ideas, or confusions, then let me know in the comments. We can have a discussion. And finally, in the video description, I'm linking an article that kind of inspired my video, and it's this 1920s mathematical teaching article where the author uses all these super flowery like language and tells these like kind of absurd stories about examples like the ones I gave, examples of where mathematicians extends concepts. They go into many examples of the why and how concepts are extended. Things like how we define a fourth dimension, or what are transcendental numbers, or why would we like transcendental numbers, or how do complex numbers work? Why is that infinity we usually don't define as a number, even though it is a useful concept? So yeah, that's it. Have a nice drink and have a nice day.